Hey everyone, Mr. Hauk here. In today's video, we're going to be looking at how we can solve simple trigonometric equations. Let's go ahead and get started. The first thing we want to do is see how we can check if certain solutions will work. So we're going to be checking trigonometric solutions. Let's begin with the example where we determine whether the angle theta equals pi over 4 is the solution to the equation sine of theta equals 1/2. So in order to check, we would simply plug in pi over 4 for theta. So we would say sine of pi over 4 equals, and we're going to use our unit circle to figure out what the sine of pi over 4 is. Well, we can see pi over 4 is right here. Sine is the y value, so the y value at the angle pi over 4 is square root of 2 over 2. So sine of pi over 4 equals square root of 2 over 2. And that is not equal to 1/2. So what that tells us is that theta equal pi over 4 is not a solution. Okay, so theta equal to pi over 4 is not a solution. Well, now let's check if theta equals pi over 6 is a solution. So we'll do the same thing here. Let's say sine of pi over 6. So we're substituting theta with pi over 6. Let's look in our unit circle. Pi over 6 is right here. The sine, or the y value of pi over 6, is 1/2. So the sine of pi over 6 equals 1/2. And would you look at that? That's exactly what we are checking. So since the sine of pi over 6 equals 1/2, that means pi over 6 is a solution. Okay, so theta equals pi over 6 is a solution. It's the green check mark of approval. Now, how can we verify that graphically? Well, the nice thing is, with Desmos or a graphing calculator, we can graph that y equals sine of theta, and we can check for what angles the y value would be 1/2. So if we hop on over here to Desmos, I've gone ahead and put in y equals sine of x. Notice I've also changed my step to pi over 6. You can change it to pi over 4. I just chose pi over 6 here. So if I look, we want to find where is the sine of x equal to 1/2. Well, if I take a second equation, y equals 1/2, and intersect it with y equals sine of x, where the blue line, which represents y equals 1/2, intersects with the red curve, y equals sine of x, that's going to be the points. Those points of intersection are going to represent the angles where those two curves, or the line and the curve sine of x, are equal to each other. So we can see right here at pi over 6, the sine of x is equal to 1/2. So that's one way that we can check that graphically. So next, let's consider the equation cosine of theta equals 1/2. And we want to write a general formula for all possible solutions and provide at least 6 solutions. And remember that cosine of theta equals 1/2. We're looking for which angles theta have cosine values of 1/2. Okay, which angles theta have cosine values of 1/2. So we want to go to our unit circle. And if I'm looking for a cosine value, which is an x value of 1/2, well, I see an x value of 1/2 here at pi over 3, and I see an x value of 1/2 here at 5 pi over 3. You can see that right there. But here's the small issue that we're going to run into. So we can definitely see at pi over 3 and at 5 pi over 3, we have cosine values of 1/2. But we haven't restricted our domain to anything. So we know that on our unit circle here, every 2 pi, so if I take pi over 3 and I go a full 360-degree rotation or a 2 pi rotation, I'm going to wind up back here with another cosine value of 1/2. So every 2 pi, I'm going to get, every 2 pi from pi over 3, I'm going to get another cosine value of 1/2. So if I added 2 pi to pi over 3, well, pi over 3 plus 2 pi, and let's think about that here. 2 pi, in this case, would be 6 pi over 3. That way we have the common denominators. So if I added 6 pi over 3 to pi over 3, I would get 7 pi over 3. If I added another 2 pi, or 6 pi over 3, then I would get 13 pi over 3. And I could keep this up. I could keep adding 2 pi, or 6 pi over 3, infinitely many times. So I could take pi over 3 plus pi over 3 plus 2 pi k, where k is representing an integer, and for whatever value of k, whatever integer k we get, that is going to give me that's going to be an angle that gives me a cosine of 1/2. And the same is going to work for 5 pi over 3. So if I look at 5 pi over 3 right here, well, if I add 2 pi to 5 pi over 3, I'm going to get a coterminal angle that's also going to have a cosine value of 1/2. So I'm going to keep adding 2 pi. So 5 pi over 3 plus 2 pi, remember again, we're going to let 6 pi over 3 represent 2 pi so that we have the common denominator of 3. So 5 pi over 3 plus 6 pi over 3, that's going to be 11 pi over 3. I could add 6 pi over 3 again, get 17 pi over 3. And I know that I could do this infinitely, keep adding 6 pi over 3. So 5 pi over 3 plus 2 pi k, again, k is representing an integer. If I keep adding 2 pi to 5 pi over 3, I'm always going to get an angle with a cosine value of 1/2. So to more specifically answer our question here, these represent at least 6 values. Okay, these are at least 6 values. Let me fix that up, it's bothering me visually. So here are at least 6 values, at least 6 possible solutions. But more importantly, here are the general formulas for all solutions. And remember, this is specific to this problem. So these are not general formulas that are always going to work. These are general formulas that satisfy the equation cosine of theta equals 1/2. So typically, in most situations, we're only going to be interested in finding solutions to trig equations on the restricted domain 0 to 2 pi. That way we don't have infinitely many solutions every single time. It's still important to take note of your restricted domain in the case that your restriction is different, as that's always going to affect the number of solutions that you have to your equation. But for these examples that we're going to do in today's lesson, we're going to keep it restricted to 0 to 2 pi. So here's the first example we're going to look at. We're going to try to solve 2 sine of theta plus square root of 3 equals 0. Okay, so what we're going to try to do is we're going to try to get theta by itself. Theta is our variable. That's what we're trying to solve for. So I'm going to begin by subtracting, begin by subtracting square root of 3 from both sides. That's going to give me 2 sine of theta equals negative square root of 3. Now let's go ahead and divide both sides by 2. Now I'm going to get that the sine of theta is equal to negative square root of 3 over 2. Again, we're trying to get theta by itself, so we know we can get rid of sine by taking the inverse sine of both sides. So theta will equal the inverse sine of negative square root of 3 over 2. So what this is really asking us, if we're trying to find the inverse sine of negative square root of 3 over 2, is what angle or angles on our restricted domain 0 to 2 pi is the y value, since we're dealing with sine, is the y value negative square root of 3 over 2. So let's turn to our unit circle and look for y values of negative square root of 3 over 2. Well, I can see a y value of negative square root of 3 over 2 right here at 4 pi over 3. And I can see a y value of negative square root of 3 over 2 right here at 5 pi over 3. So our answer would be, since we have more than one answer, we're going to answer them as a set. So the angles that make this work are the angles 4 pi over 3 and 5 pi over 3. Again, since we have multiple answers, we are answering them as a set. Now, we can check that graphically. Part of our AKS here is to be able to verify solutions graphically. So let's check in Desmos here. So I've gone ahead and pre-populated Desmos. We're going to check 2 sine of theta. Now in Desmos, we always want to use x as the variable, even though the problem says theta, we use x. So 2 sine of x plus square root of 3. And we want to check where does our sine curve here cross through the x-axis. It's going to cross through at 4 pi over 3 and 5 pi over 3. And notice I would have infinitely many solutions, but we are cutting off the domain at 2 pi. So the only answers between 0 and 2 pi are 4 pi over 3 and 5 pi over 3. All right, in our next example, we want to solve 2 cosine of t plus 3 equals 2. This time our variable is t instead of theta, so t is representing the angle now. But our goal is still the same. Let's try to get t by itself. So we'll begin by subtracting 3 from both sides. This is going to give us 2 cosine of t equals negative 1. Let's divide both sides by 2. We're going to get cosine of t equals negative 1/2. And since we're trying to isolate for t, we know that if we take the inverse cosine of both sides, that'll get rid of the cosine on the left. So the angle t is equal to the inverse cosine of negative 1/2. So again, what this is really asking us is for what angle or angles, there could be multiple angles, t, on the restricted domain 0 to 2 pi, is the x value, since we're working with cosine, negative 1/2. So moving over to our unit circle, we want to find x values of negative 1/2. Here's an x value of negative 1/2 at 2 pi over 3, and here's another x value of negative 1/2 at 4 pi over 3. So our answers, since we have 2 of them, are going to be the set 2 pi over 3 and 4 pi over 3. All right. Moving to our third example, we want to solve, or actually real quick, let's go ahead and check that with Desmos, part of our AKS there. Notice that in Desmos, the equation that I'm graphing is 2 cosine of x plus 1. And if we look at the equation was 2 cosine of t plus 3 equals 2. When you enter an equation into Desmos, you want to go ahead and make one side equal to 0. So all I did was subtract 2 from both sides, and that changed this into a plus 1. And that's what I'm putting into Desmos. Okay. Just a quick note there about how to use your graphing calculator. So 2 cosine of x plus 1, and we can see the solutions between 0 and 2 pi are 2 pi over 3 and 4 pi over 3. All right, moving on to our next example, which is the tangent problem. We want to solve 3 tangent of x plus 2 square root of 3 equals the square root of 27. Once again, our goal is to get x by itself because x is now the variable. So we want to go ahead and subtract 2 square root of 3 from both sides. One thing that might benefit us real quick though is let's go ahead and reduce square root of 27 or simplify it. So we're going to have 3 tangent of x plus 2 square root of 3. And if let's do a little bit of side math here. I'll do this up in red. Square root of 27, well, 27 is 3 times 9. 9 is 3 times 3. So we would have 3 3's underneath the square root, and this would simplify to 3 square root of 3. Okay, so this is 3 square root of 3. All right, now let's go ahead and subtract 2 square root of 3 from both sides, because again, we're trying to isolate for x. And what this is going to do is we're going to get 3 tangent of x. Well, when we think about 3 square root of 3 minus 2 square root of 3, they share the same radicand, square root of 3. So we're just going to have 1 square root of 3. And now let's divide both sides by 3. And we get that the tangent of x is equal to square root of 3 over 3. To get rid of tangent, we'll do the inverse tangent of both sides. So x is equal to the inverse tangent of square root of 3 over 3. And once again, just to keep in mind what this is really asking us for, it's asking us for what angle or angles x from 0 to 2 pi is the tangent square root of 3 over 3. All right, let's look at our unit circle. So we're looking for tangent values of square root of 3 over 3. On our unit circle here, the values in the boxes are the tangents. So at pi over 6, we have a square root of 3 over 3. And at 7 pi over 6, we have a tangent value of square root of 3 over 3. So our answers here, since there are more than one, I'm going to put them in a set. X is the set of pi over 6 and 7 pi over 6. And once again, let's double check that graphically. For this graph, I'm putting 3 tangent of x minus square root of 3. Remember once again that to use Desmos, we need to go ahead and make one side of the equation equal to 0. So I subtracted the square root of 27, which remember was 3 square root of 3 from both sides, and that made this side 0. So that's what I'm graphing right here. And we can see that the answers, the solutions, between 0 and 2 pi are pi over 6 and 7 pi over 6. All right. Next, we want to solve 2 sine squared of theta minus 1 equals 0. And this one's going to be a more interesting example because we have a squared trig function. But still, let's go ahead and try to get the theta, which is our variable now, by itself. We're going to begin by adding 1 to both sides. So plus 1, plus 1. This is going to give us 2 sine squared of theta equals 1. Let's go ahead and divide both sides by 2. And we get sine squared of theta equals 1/2. And we know if we want to get rid of a power of 2, we can take the square root of both sides. Now here's where we have to be a little bit careful. On the left side, sine, the squared power of 2 and the square root, they cancel each other. We just get sine of theta. On the right side, when you take the square root of a number, you have a plus or minus that goes in front of it. So we have plus or minus square root of 1/2. Well, let's start to do some simplifying here. Square root of 1/2 is, the square root of 1 on top is 1, but we can't take the square root of 2. And we also don't like square roots in the denominator, so let's go ahead and multiply root 2 over root 2. And this is going to give us plus or minus square root of 2 over 2. So we are looking for, essentially, if we take the inverse sine of both sides, theta is equal to the inverse sine of plus or minus square root of 2 over 2. So we are looking for what angles theta between 0 and 2 pi is the y value either positive square root of 2 or negative square root of 2 over 2. So if we look on our unit circle, again, we want y values that are either positive square root of 2 over 2 or negative square root of 2 over 2. What pi over 4, we have a positive square root of 2 over 2. At 3 pi over 4, we have a positive square root of 2 over 2. At 5 pi over 4, we have a negative square root of 2 over 2. And at 7 pi over 4, we have a negative square root of 2 over 2. So all 4 of those angles are the solutions. So theta equals the set pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. 4 solutions here. All right, so checking this one, again, always a good idea to check our answers using Desmos here. And go away. There we go. So, oh, I don't think it's going to reset it. Yep. All right, well, that's fine. let's go ahead and put in 2 sine squared of x, there we go. And then minus 1, we already have it equal to 0, so we don't need to worry about that part. Let's change our step to something like pi over 4. And let's see what happens. Between 0 and 2 pi, we can see we have a solution at pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Once again, those solutions are where the sine, where the curve is crossing through the x-axis. All right. In our next example, we're going to have another problem that involves a squared. So we have 4 cosine squared of t equals 1. Let's go ahead and work on getting the t by itself. So I'm going to divide both sides by 4. This is going to give me cosine squared of t equals 1/4. We want to get rid of the squared, so let's take the square root of both sides. We get cosine of t equals plus or minus the square root of 1/4. Well, square root of 1/4 is 1/2, because square root of 1 is 1, square root of 4 is 2, so we get plus or minus 1/2. Don't forget that plus or minus, that part's pretty important. And what this means is that if we take the inverse cosine on both sides, that t is the inverse cosine of plus or minus 1/2. So we're looking for all angles t from 0 to 2 pi, where the x value is either a positive 1/2 or a negative 1/2. And if we go through and look at all the angles on the unit circle, we would end up getting these 4. We would get pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. Once again, we can check with Desmos. I'm going to save us a little bit of time by not checking for this one here, but we would make sure to subtract the 1 from both sides, and you would graph 4 cosine squared of t minus 1, and you would see that these are our the 4 places where the cosine curve would cross through the x-axis. All right, and then next example. Suppose that f of x equals 4 tangent of x, and we want to solve f of x equals negative 4. Well, the problem looks slightly different, but it's really not any different here. We're going to make a substitution. We're going to substitute f of x with negative 4. So this f of x is going to get replaced with negative 4, which is equal to 4 tangent of x. And from here, we're going to do our usual stuff. Let's divide both sides by 4. We would get negative 1 equals the tangent of x. And taking the inverse tangent of both sides, we get that the inverse tangent of negative 1 equals x. So this is really asking us for what angle or angles x from 0 to 2 pi is the tangent negative 1. If we look on the unit circle, tangent values of negative 1 occur at these angles 3 pi over 4 and 7 pi over 4. And once again, you could double check that in Desmos. You would just make sure to set this equal to 0 by adding 4 to both sides. So you would graph 4 tangent of x plus 4. All right, the last problem we want to consider is an application problem. And it's an application problem involving what many of us have probably taken a ride on at some point in our lives, which is the Ferris wheel. So in 1893, George Ferris engineered the Ferris wheel. It had a diameter of 250 feet, and if the wheel makes 1 revolution every 40 seconds, then this function represents the height of a seat in feet on the wheel as a function of time in seconds. We want to figure out, during the first 40 seconds of the ride, at what time t is an individual on the Ferris wheel exactly 250 feet above the ground. So I made a couple notes here. During the first 40 seconds of the ride, well, we've already been told that 1 revolution is 40 seconds. So during the first 40 seconds of the ride, we're just really looking at the first revolution. And we're also being told that we're looking for when the Ferris wheel is 250 feet above the ground. Well, remember that h of t represents the height. So 250 is going to be what we plug in for h of t. So I went ahead and set it up. 250 equals 125 sine times sine of 0.157t minus pi over 2 plus 125. And this looks pretty messy, but if we handle it piece by piece, it actually turns out to be pretty easy to solve. So let's go and see what would end up happening here. First thing I want to do is I want to subtract 125 from both sides. This is going to give me 125 equals 125 sine of 0.157t minus pi over 2. The next thing I want to do is divide both sides by 125. That's going to get rid of this coefficient. So 125 divided by 125, that's just 1. And then the 125s here will cancel. We just get sine of 0.157t minus pi over 2. In order to get inside the parentheses here, we need to get rid of sine. So we're going to have to take the inverse sine of both sides. So the inverse sine of both sides, we get inverse sine of 1. But when we take the inverse sine of the right side, the sine will cancel with the inverse sine, and we just get 0.157t minus pi over 2. And now we can continue solving for t. Let's go ahead and add pi over 2 to both sides. Oh, and by the way, thinking about the inverse sine of 1, we're looking for an angle where the sine value is 1. And if you look at your unit circle, there's only one angle from 0 to 2 pi that has a sine value of 1, and that's pi over 2. So the inverse sine of 1 is going to be pi over 2. So we're going to be adding pi over 2 to both sides. So pi over 2, let's just go ahead and write this step down right here. All right, so add pi over 2 to both sides. Pi over 2 plus pi over 2 is going to be 1 pi. So pi equals 0.157t. And then lastly, we would divide the 0.157 on both sides. And if you put that into your calculator, you're going to get that t is approximately equal to 20 seconds. Now, let me show you how we can use technology, Desmos, to verify that. It's actually pretty cool how it works. So what we're going to do, let's go ahead and get rid of this here. Let's put in the equation that we started with, which was 125 sine of 0.157t, 0.157, again we're going to use x instead of t, minus pi over 2, plus 125. And we can't see the graph very well because most of it is pretty high up there in the coordinate plane. But what we want to do is we're trying to find the time where an individual receipt is 250 feet above the ground. So if we take this and we say, okay, well, I want the height, which in this case is y, to be equal to 250, and I start to zoom out, we can see right here in the first 40 seconds that at 20.01 seconds, or essentially 20 seconds, that the height is 250. And that's exactly what we got here when we did all the math. Now, there's also a more logical way to think about this. If we're thinking that one revolution takes 40 seconds, and we already know the diameter is 250 feet, well, think about, if we have a seat that's starting on the ground, it takes 40 seconds for it to go full circle on the Ferris wheel. Halfway through that rotation, it's going to be at the very top, which the diameter here is 250. We know that means after 20 seconds, which is half of the full revolution, we'd be at the tippy top, 250 feet. Half of 40 seconds is 20 seconds. So that's kind of a more logical way to think about that.